Hello and welcome. My name is Noah Deer. Today we are doing lesson 4 of our fourth term calculus sequence, and we're going to be looking at velocity and acceleration, specifically of space curves of vector valued functions. Start by doing just some definitions and looking how we can take derivatives to find velocity and acceleration. We'll do some applications or situational initial conditions, if you will, as it's titled here, but really we're just going to be setting up space curves and then being able to take their derivatives and talking about the velocity and acceleration, or maybe taking an antiderivative if we're given a velocity space curve. So then we'll look at tangential and normal components of acceleration, which is just essentially the direction of the acceleration in a moment in time, or the right angle direction. So it's kind of the normal component is saying essentially how tightly the curve is turning. And then we will look at minimizing speed. So if we have a velocity function, we will then go ahead be able to take its derivative and find its length and find the minimum of the length there. So yeah, we will get into those in just a second. So let's just start with the basics though. We have our definitions. So normally we have a displacement function such as s of t, and this would just be in one dimension, so we could have something like s of t equals t squared plus 3t minus 1. Doop. And, oops. And that's great, and we could take the derivative and say that our velocity function is then 2t plus 3, right? And then our acceleration is just 2. And this is how we would do this in one dimension. But we are really going to be looking at doing these with space curves in 3 dimensions. So we have a position vector, r of t, equals f of t, g of t, h of t, which is giving our x, y, and z components. And then our velocity is simply defined as the derivative of the position function. And our acceleration is defined as the derivative of the velocity. So we have our first derivative of f, first derivative of g, first derivative of h over here, and then we have our second derivative of f, second derivative of g, and second derivative of h over here, which I hope is expected at this point. Let's go ahead and take a look at a specific example here. So if I have r of t equals 2 minus t comma 4 square root of t, note we're just doing this in 2 dimensions just to get ourselves started. We will do it in 3 dimensions with GeoGebra in just a little bit. So first thing, what's the velocity function? So v, whoops, control, there we go. V of t equals, well, if I take the derivative of 2 minus t, I just get negative 1. And the derivative of 4 root t is going to be 2t to the negative 1/2. Remember that the square root of t is just t to the 1/2 as we take that derivative there. And our acceleration function now is going to be 0, and then negative t to the negative 3/2 as we pull that negative 1/2 down there and cancel the 2 and subtract 1 here. So now we have our velocity and acceleration functions, and we will use those in a minute to go ahead and look at the velocity and acceleration of our position of our space curve at a specific point in time at t equals 1 here. So to start, we're going to just say, what does the graph of r of t look like? And to do that, I'm going to kind of think about what we did in previous lessons. We can note that the domain has to be t is greater than or equal to 0. So I'll plug in 0, just get our starting point of 2, 0. And plug in maybe 1. I'll plug in 4. And I'm doing this because it's a square root function, so I'm just picking values for t that I can take the square root of easily. So we have this is 1 comma 4, and this is negative 2 comma 8, negative 2 comma 1, scale here. Oops. And sorry about that, finicky software. But it looks like we are going to have a curve that has this kind of shape here. And so this is when t equals 1 is at this point. Okay, great. So now we want to know at t equals 1, what is our velocity and acceleration vectors? So I'm going to do this right here. V of 1 equals -1, 2. And A of 1 equals 0, -1. So if I plot these vectors starting from this point, right, we don't want to do this from the origin. We want to plot our velocity and acceleration vectors from this point. So here I'm going to go -1 in this direction and then 2 up. So this is the vector v of 1. And we can see that that's the direction of our curve here. And my acceleration is 0, -1. And this vector is showing how the curve is turning. It's giving us an indication of the change in the velocity. So the velocity was straight in this direction, and now it's moving off. But the acceleration is saying that the velocity is moving to the left, right? So our velocity was here, and the acceleration shows the change in velocity, which is moving to the left. And that's essentially it. We'll look at this same idea in 3 dimensions. But for now, let's go ahead and just give you guys a chance to do this one. So try this out, and I will come back in just a few seconds to go ahead and show you the answer. So pause the video now and work through exercise 4.1.1. All right, so it's been just a few seconds in computer time, but in our time we just spent a few minutes working on this. And I have here, I found the velocity function by taking the derivatives here. So we have v of t equals -3 sine of t in the I direction plus 2 cosine of t in the j direction. The acceleration function a of t equals -3 cosine of t in the I direction and -2 sine of t in the j direction. I then said, okay, I want to get some points on here, and I'm pretty familiar with this function. This is helping me recognize that this is the equation of an ellipse. So when t is 0, we get 3i. I'm actually going to skip the pi over 3 in my explanation here for a second, but we have r of pi over 2 equals 2j, r of pi equals -3i, and then r of 3 pi over 2 equals -2. And if we plot those 4 points, r of 0 equals 3 is 3, 0 over here. R of pi over 2 is 2j, so I have 0, 2, this point here. And then I have -3i when t is pi, and so I have -3, 0 right here. And then r of 3 pi over 2, I get -2, and this gives me this point here. And this is a good indication that we just have this shape. You're welcome to plug in more time values to really ensure that you know that this is what's happening. It's actually nice for me to just go ahead and add some directional arrows so we can see that in time we're moving in this. So then we have r of pi over 3, and when I plug that in we get 2i plus square root of 3j. So that's this point here. This happens when time is pi over 3, or t is pi over 3, if we're not talking about time necessarily. And then my velocity function v of pi over 3 gives me -3 root 3 over 2 in the I direction plus 1j. So I can go ahead and graph that vector there. And we see that's the direction of motion. That is the direction of the velocity. And the length of the velocity vector is going to tell me how fast we're really going at this point in time. The acceleration vector, a of pi over 3 is negative 3 over 2 in the I direction, minus root 3 in the j direction. We see that's pointing straight back at the origin. So this origin is somehow like a gravitational center that's pulling this particle around in this ellipse shape here. So yeah, that's it for that problem. Let's move on to 3 dimensions. So in this example, we're actually going to do some backwards movement, and we're not going to look at any graphs right now. This is just more for computational purposes. So we're given an acceleration function, a of t equals 2I plus 6tj plus 12t squared k, and we are given initial conditions that the velocity at time 0 equals I, or 1I, and the position at time 0 equals j minus k. So if we want to find our velocity vector, we can essentially just take the antiderivative of a of t. So looking right here, I say v of t is going to equal 2t in the I direction. Just taking the antiderivative of 2 gives me 2t in the I direction. We're doing this component-wise again. And the antiderivative of 6t is 3t squared in the j direction, plus 4t to the third in the k direction, right? Because 3 times 4 is 12. So this is my velocity function, except for we can have some other vector. I should be doing this in ijk form. So I can have some other vector being added to this. So this is like adding c when we were taking the antiderivatives in second term calculus and integral calculus, right? So when we have that plus c on the end, now it has to be a plus a constant vector. And we could also do this as 2t plus a in the I direction. Altogether here, 3t squared plus b in the j direction plus 4t cubed plus c in the k direction if we wanted to do this individually. But we just have to remember when we take the antiderivative, there's a constant that we need to add to our antiderivatives. And this being the case, we recognize that if I was taking the derivative to get the acceleration, this entire vector over here, ai plus bj plus ck, is going to go to 0. And when we take the derivative of this part over here, we're going to get back to exactly where we started, just like we want. So if I want to find what a, b, and c are, I need to use this initial condition that v of 0 equals I. So I'm going to plug in I over here on the left, and I'm going to plug in 0 for t, right? So v of 0 equals 0 in the I direction, 0 in the j direction, 0 in the k direction, plus ai plus bj plus c in the k direction. And looking at this, we see that it has to be that a equals 1 and b equals 0 and c equals 0, just by matching our components, right? We have on the left here 1i, so a has to be 1. We have nothing else. We have 0j, 0k on the left, so b and c both have to be 0. And this gives us that my velocity function has to be, I'm going to bring this together. I'm going to bring this as 2t plus 1 in the I direction, plus 3t squared in the j direction, plus 4t to the third in the k direction. All right, and we're going to just now repeat this in order to get our position function. Our general position function is going to be t squared plus t plus some new constant. I'm going to call this a2 in the I direction, plus t cubed plus b2 in the j direction, plus t to the fourth plus c2 in the k direction. And I'm just using a2, b2, and c2 to distinguish that these are different than the a, b, and c's that we had up here before. Now we need to find my A2, B2, and C2, and we do that by using our initial condition that R of 0 equals J minus K. So J minus K is what R of 0 equals, and I'm going to plug in 0 now for t on the right side, and I get A2I plus B2J plus C2 in the k direction. And now we can do component matching. So A2 has to equal 0, B2 has to equal 1, and C2 has to equal -1, because our component for J is 1 and our component for K is -1. And this gives us our position vector for this initial condition of R of t equals t squared plus t in the I direction plus t cubed plus 1 in the j direction. Note I'm just plugging in this b1 value right here. And the c2 value I'm going to plug in right here. So t to the 4th minus 1 in the k direction. And that's it. That's our velocity and position vectors for these initial conditions specifically. So we'll go ahead and have you guys give one a shot, and in just a few seconds I will come back and show you the solution to this so that you can check your answer. Go ahead and pause the video now, and I will be talking to you again in just a few moments. Alright, and boom, here is our solution. We take the antiderivative of A to get the vector -3t plus a1, comma b1, comma -5/2 t squared plus c1. We have our initial condition that v of 0 equals 1, 2, 0. So we plug in 1, 2, 0 equals, and I plug in 0 for t in the generalized velocity vector function we have here, and we get a1, b1, c1. And thus a1 equals 1, b1 equals 2, and c1 equals 0. Plugging those back into the generalized form, we get v of t equals -3t plus 1, comma 2, comma -5/2 t squared. We then take the antiderivative again to get our position vector function, and we get -3/2 t squared plus t plus a2, comma 2t plus b2, comma -5/6 t cubed plus c2. And plugging in our initial condition that R of 0 equals 0, 0, 10, we get 0, 0, 10 equals A2, B2, C2 by plugging in 0 for t's in the previous line. Thus A2 is 0, B2 is 0, and C2 is 10. And we can plug those back into our generalized position vector function and get R of t equals -3/2 t squared plus t, comma 2t, comma -5/6 t cubed plus 10. And that is our solution. All right, so let's go ahead and move on to situational initial conditions, which is really just applications of exactly what we've been doing, where we're going to look at an acceleration function, vector valued function, and then be able to use that with initial conditions to come up with velocity and position, and tell that something about use that to tell something about a specific situation. So our first example that we're going to look at is a batter hits a baseball 3 feet above the ground towards the center field fence, which is 10 feet high and 400 feet from home plate. The ball leaves the bat with a speed of 115 feet per second at an angle of 50 degrees above the horizontal. We want to know, is it a home run? Go ahead and pause the video if you want to and just read through this a couple times, make sure you're seeing what's happening. As I look at this problem and start thinking about how I want to draw a picture, which should always be the first thing that we do in any sort of story problem, is I'm recognizing, okay, I've got home plate here, the ball is hit 3 feet off the ground, it's being struck with an initial velocity of 115 feet per second, that is v of 0. And at an angle of 50 degrees, And there's no three-dimensional component to this. It's not worrying about an angle to the left or right. It's going straight back towards the center field fence. So I don't have to worry about all three dimensions. But we know that the fence is 400 feet away and that the fence is 10 feet high. And please note, this is not the scale by any means. This is horrible as far as scale goes. But it has all of the information included here. So we actually, even though we're given information about velocity, I actually want to start by talking about acceleration, because the acceleration for this situation is going to be 0 in the x direction. Let's think about this. So if I'm saying this is my x direction from left to right, so here we have x is 0 and x moving left to right. Once the ball is struck, no other force is acting on it that is described in the problem. Yes, there's probably air resistance and maybe some wind is going to affect it, but none of that is given in this problem, so we just want to assume 0. So yes, this problem is only giving us an estimation for what's really going to happen, but it's going to give us a pretty good estimation for that. So we'll then look at the y component for the acceleration and note that that should be negative 32 because gravity in feet per second squared is negative 32 feet per second squared, and that is an approximation. But that's the only acceleration that's affecting the ball in the downward direction, and while it's not described in the problem, we should hopefully have some understanding at this point that that is a gravitational constant that we're going to use in a lot of these story problems. So this is where we start. And then from there, we can start building our velocity and our position functions using some initial, like we have our initial condition for our velocity. Need an equal sign here. And now I can say, okay, how am I going to get my velocity? Well, if I take the antiderivative of 0, I'm just going to get some a1. And then here I'm going to get negative 32t plus b1. And I need to know what are these initial conditions. Well, we know that, I'm forgetting to note that this is actually the magnitude of the velocity, not the velocity itself. It's not just 115 feet per second. It's 115 feet per second at an angle of 50 degrees from the horizontal. So what this is saying is that v of 0 is going to be 115 cosine of 50 degrees in the x direction and 115 sine of 50 degrees in the y direction. So this is my initial condition by just looking at the x and y components of my velocity vector with this 50-degree angle and magnitude of 115 feet per second. And I'm going to leave these in exact form because I don't want to do any rounding and then have the, if I round now and then do some arithmetic on it and then round again later, I then have compounded my error via that rounding multiple times. So I'm not going to round until the very end of the problem. That's something that you should always keep in mind and keep as a rule for all of your story problems and any time that you're trying to round. Just don't do it until the very end as a rule. So here I can use this and say, okay, v of 0, if I plug 0 into my generalized velocity function, I get a1 comma b1, and so we can quickly see that a1 b1 is exactly these components. So v of t for this situation is in fact 115 cosine of 50 degrees and then negative 32t plus 115 sine of 50 degrees. And this actually makes sense for our velocity. We know that our x component for velocity is just a constant. It's not being affected by anything. So my velocity in the x direction just stays at this value. In the y direction, we know that it's going down by 32 feet per second squared every second, but it starts at this 115 sine of 50 degrees. So it's really 115 sine of 50 degrees to start, and then subtract 32t every second. All right, and from here we're going to go ahead and find our position. Oops, r of t. Let's make that clearly an r. So I start taking my antiderivatives, and I get 115 cosine of 50 degrees times t plus a2, and then negative 16t squared plus 115 sine of 50 running out of space, t plus, hopefully you guys are okay with that. That's all in that component there, plus b2. And my initial conditions for position, we have r of 0 is 0, 3, right? So if I plug that in over here, I have r of 0 equals a2, b2. And so a2 has to be 0, and b2 has to be 3, so my generalized position function, my specific position function for this initial condition is 115 cosine of 50 degrees times t, a2 is 0, comma, negative 16t squared plus 115 sine of 50 degrees times t plus 3. Great. What we want to know is this a home run? So let's see, I'm running out of space here. This pen definitely writes too big on this screen. What we want is essentially to find how long it's going to take for the ball to get 400 feet out in the horizontal, and then plug that time in for our y component to see if it is greater than, or really strictly greater than 10 feet, right? We don't want it to hit that edge of the fence. So let's see if I can't squeeze this in over here. If I say 400 equals 115 cosine of 50 degrees times time, then we get t equals 400 over 115 cosine of 50 degrees. I then take this value and plug it in for t into my y component to see what we get. And then we will write our conclusion. So we are going to take, so this time is, we'll say t sub 400 for that being the x component. So y sub 400 for the x component. This is going to equal negative 16 times 400 over 115 cosine of 50 degrees squared plus 115 sine of 50 degrees times 400 over 115 cosine of 50 degrees squared plus 3, and we'll plug this into the calculator. Oh, this should not be squared in this bit after the sine of 50 degrees. My bad. Come on, where's the eraser? No. Alright, so I am plugging this in off to the side, and I am getting 11.20 as the number of feet. Keep our units here. And so my conclusion, finally, where am I going to squeeze this in, is yes. Oh, of course. No, I want that. Yes. It is a home run. Clearing the fence. just 1.2 feet. And yeah, so that's what we need to do. We often start with our acceleration as a key thing here. So really remember that when we're doing this, we know acceleration in the x and y directions, and we can then take the antiderivative to get our velocity, and then we think about the situation and what is our initial conditions for velocity, take the antiderivative again, what are our initial conditions for our position, plug those in, and finally get a position vector valued function. So then we have to stop and think, okay, how does this actually answer the question? Now that we have our position function, we have to know, is it a home run? So we know it's a home run if, when x is 400 feet out, that the y value is bigger than 11.2 feet. And that would be, yeah, that's how we want to look at this. Okay, go ahead and let's scroll down here. You guys give this one a shot, and I will come back and talk you through it in just a few moments. All right, so a lot of things are going on here. We're going to start with the same idea. We're going to note that we are in meters instead of feet, so our acceleration function is going to be still 0 in the x direction and negative 9.8 meters per second squared in the y direction. Over here, if we look at our picture, we actually aren't given an initial height, so I'm just labeling this h naught. That's going to be kind of a problem that we have to deal with in this entire exercise here. So we know that the ball hits the ground 90 meters away from where it was hit. We are not given the initial velocity, so I'm just giving that a variable because that's what we're trying to find. So I want to give it a variable so I know how to find it. The angle that it is thrown at from the horizontal is 45 degrees, so I've just got this all labeled. Then go back over here to my acceleration and say, okay, my velocity has to be the antiderivative of this, which is a1 comma negative 9.8t plus b1. We know that my initial velocity, which we're just calling v naught, has to be v naught cosine of 45 degrees, comma v naught sine of 45 degrees. Just looking at our picture, we don't know what v naught is, but we can still say that my initial velocity is component-wise, whoops, so finicky when I put my hand on here. Switch that back over. That the y component is v naught times sine of 45, that the x component is v naught times the cosine of 45 degrees. And we know cosine and sine of 45 degrees are both square root of 2 over 2, so I've gone ahead and plugged those in to use those values here. Now I can take these and plug them back in for my a1 and b1, because we know v of 0 should be a1, b1 also, looking at this previous line. So I'm plugging those back in and seeing that my velocity function should equal v naught root 2 over 2, comma, negative 9.8t plus my b1 value, which is v naught root 2 over 2 again. Okay, so now we have my velocity in terms of the initial velocity, and that's nice. We want to eventually get solved for v naught, and to do that, we know that the ball lands 90 meters away, so we need position function somehow. We're not sure how yet necessarily, but next logical step should be need the position function. So I take the antiderivative again, and get v naught root 2 over 2 times t plus a2, comma, negative 4.9 t squared plus v naught root 2 over 2 times t plus b2. Okay, so that's my general antiderivative of my velocity function. We know that the initial position is 0 comma h naught, and we don't know h naught, but I'm just saying that is my initial height. Right? I've said that over here. Also, I've defined it. Let h naught be the initial height that the ball is thrown from. So now my position function, my a2 has to be 0. When I plug in 0 for t, I get a2 has to be 0. When I plug in 0 for t over here for my initial position, I get b2 alone equals h naught. So I plug in 0 for a2, h naught for b2 to get my specific initial position function of v naught root 2 over 2 times t, comma, negative 4.9 t squared plus v naught root 2 over 2 times t plus h naught. Great. And we don't know h naught, and that's okay. We know that the final position of the ball is 90 meters in the x direction, 0 meters in the y direction. If I plug in 90 for my x position, I get 90 equals v naught root 2 over 2 times the final time, the time when it hits the ground. So I'm letting t sub f be the time at which the ball hits the ground. If I solve for t sub f, I get it equals 90 root 2 over v naught. And then if I look at my y component of my position, my y final is 0. So if I set this equal to 0, right? If I take this, my y component, and set it equal to 0 and plug in my final time at the same time. So I'm plugging in this final time in for t here, and then I'm solving for v naught. Now I have two variables here. I still have v naught and h naught, but I'm just solving for v naught generally in terms of h naught. And so this is my initial velocity depending on how high that we are hitting, or that we're throwing the ball from. And the reason that this depends on the height is because if it has a couple of extra meters to fall to the ground, that means that to get 90 meters, it actually didn't need to go quite as fast because it had more time to fall to the ground, right? So if we are throwing this off of an even higher and higher kind of thing, we look in this function and we see as h naught gets bigger, that actually shrinks our v naught. We don't need to throw it as fast to start if we are higher up to get it to go 90 meters essentially. So that's good. This actually makes sense in context. So if we look for a specific one, which it was not asked for, but I figured, hey, let's plug in an initial height of 4 feet. Maybe you plugged in an initial height of 0 feet, and you took that for granted as just a 0, or you plugged in 5 feet because you thought, my arm's maybe 5 feet off the ground, and so you just did that as an estimation. That's great. I just chose 4 feet. I don't know how tall this person, maybe it's a 5-foot tall person that's throwing this ball, sure. And so then I just write out my conclusion. The initial velocity of the ball was the square root of 9.8 times 90 squared over h naught plus 90, which is about 29.06 meters per second if the initial height was 4 feet. So I'm not just stating this 29.06 as the answer. I'm stating it's the answer if the initial height was 4 feet. All right, and that's that exercise. All right, with that, we're going to go ahead and move on to a couple more applications still, but now we want to just work within 3D. So I'm just going to give a basic idea here. The exercise is going to be a little bit more difficult in how you set it up, but just keep in mind that the idea is the same as what we did in the two-dimensional situations. For example 4.2.2, what force is required so that a particle of mass m has the position function r of t equals ti plus t squared j minus 3t squared k? So we just need to remember here that the force equals mass times acceleration, or if we want to keep this with our time, we have the force vector given some input t equals mass times the acceleration vector with some input t. So we really just need to find our acceleration vector function here. So given r of t equals ti plus t squared j minus 3t squared k, we have our velocity function v of t equals I plus 2tj minus 6tk. And that's just by taking the derivatives of the components of our position function. We can then just go one step further so that our acceleration function is, when we take the derivative of 1I, we just get 0I. Go ahead and put that in just so that we can remember that we are in 3 dimensions, but we really don't need to be putting this. The derivative here is plus 2j and minus 6k. So our force function needs to be f of t equals m parentheses 2j minus 6k. And note that I left out the 0i in this case. Note also that if we worked backwards from our acceleration function, that this position function is for specific initial conditions where our initial velocity is 0, 0, 0, and our initial position is also 0, 0. So this force function and this acceleration function is generalized for a lot of different initial velocities and initial position functions. But this is the force function for this position function indeed. Okay, so that's just a quick basic there. As you look at exercise 4.2.2, you're going to need to set up an acceleration function, a force. You're going to need to set up a force function, force vector function that has an x, a y, and a z component to it now. So get your free body diagram drawn up in 3 dimensions and then get that forcing vector function and then work backwards from there to be able to find your position function. And that's going to be your general strategy. Go ahead and give that a shot. Alright, so let's take a look at the solution here. You may have laid this out a little bit different than me. Go ahead and take a look at the final answer. The ball lands about 23.43 meters west and 79.53 meters south with a speed of about 33.679 meters per second. So if you got that same answer, then you're doing great. Let's now back up and I'm going to just go through everything that I did here. So my force diagram, my free body diagram right here on the top left, I've got this diagram. I've got a force vector to the left, and that force, this is due to the wind, equals negative 4, 0, 0. And then I have a force vector heading down in the south direction, or I'm sorry, not the south direction, in the downward direction due to gravity. So the force due to gravity equals 0, 0, negative 9.8 times 0.8. So there's my free body diagram. So my total force is going to be the sum of these two. And when I add those two force vectors together, I get negative 4, 0, negative 9.8 times 0.8. And that equals 0.8 times my acceleration, because our total force equals mass times acceleration, the mass being 0.8 kilograms. So my acceleration vector now is a of t equals negative 4 divided by 0.8, 0, negative 9.8, which equals negative 5, 0, negative 9.8. So we can then start taking our antiderivatives to work backwards towards our position function. We take the antiderivative of the acceleration vector and we get v of t equals negative 5t plus a1, b1, negative 9.8t plus c1. Now we have to look at what our initial velocity is. We're given that the initial velocity is due southward with a velocity of 30 meters per second and an angle of 30 degrees to the ground. So I drew a diagram in 3 dimensions here. I have my x-axis, my y-axis, and my z-axis, and I show my initial velocity vector coming off with an angle of 30 degrees off of the negative y-axis, the negative y being a southward direction, the x being a eastwardly direction for the positive x-axis. If I look at that, and we know that the initial velocity is 30 meters per second, the magnitude of that velocity, then we know that the x direction, there's no velocity because it's being thrown due southward. My y direction, my initial y velocity, is going to be negative 30 cosine of 30 degrees. It's negative because we're going in the southward direction. The z direction, then, we are throwing it upwards, so it's a z direction, an initial z velocity of 30, sine of 30 degrees. And those simplify down to where the initial velocity vector is 0, negative 30, root 3 over 2, 15. When we set that up then, v of 0 equals 0, negative 15 root 3 after reducing, 15, then we get that a1 has to equal 0, b1 equals negative 15 root 3, and c1 equals 15. We plug those back in and we get v of t equals negative 5t, comma negative 15 root 3, comma negative 9.8t plus 15. We then take the antiderivative again, and we get r of t equals negative 5 halves t squared plus a2, comma negative 15 root 3 times t plus b2, comma negative 4.9 t squared plus 15t plus c2. For this problem, we want to keep this as simple as possible. We're going to assume that the initial position is at the origin 0, 0, 0. While in a previous problem we said that we didn't know the initial height, here we're going to say that the initial height is at 0 meters so that we can just focus on the computations here and not get caught up in a bunch of algebra. So if we have the initial position of r of 0 equaling 0, 0, 0, then we get a2 equals b2 equals c2 equals 0. Thus my position function is r of t equals negative 5 halves t squared, comma negative 15 root 3t, comma negative 4.9 t squared plus 15t. Now going back over here to the left, I've continued my work here. I say the ball hits the ground when z equals 0. So I set the z component, negative 4.9 t squared plus 15t equal to 0, and factor out a t and solve for the other t. We see that z equals 0 when either t equals 0 when we first throw the ball, or when t equals 15 over 4.9 once we've solved for t. We can then take this time and plug it into our velocity vector function and our position vector function to find our initial velocity. Now we're asked for the final velocity, not the initial velocity. And we're asked for the speed, so we take the magnitude of the velocity when the time equals 15 over 4.9. And so we get the magnitude of v of 15 over 4.9 equals the magnitude of the vector negative 75 over 4.9, comma negative 15 root 3, comma negative 15, which is approximately 33.679 meters per second, which I did by just plugging this into my calculator. We can then take the 15 over 4.9, plug it into our position function, and get r of 15 over 4.9 is approximately negative 23.43, comma negative 79.53, comma 0. Again, I got that from plugging in the 15 over 4.9 into the components of r of t, and then having my calculator simplify that down for me. And then I state my conclusion. Once again, the ball lands about 23.43 meters west and 79.53 meters south with a speed of about 33.679 meters per second. And we get the west from the negative x coordinate and the south due to the negative y coordinate here. All right, and that's that problem. All right, let's keep going down here, and we want to start talking about the unit tangent vector, the unit normal vector, the curvature, and the acceleration now. So we've already talked about the unit tangent function, how that is r prime of t over r prime of t's magnitude, and then the normal vector, the unit normal vector, is the derivative of the unit tangent function divided by the magnitude of the unit tangent function, and that division here is again to get us a unit vector. And then we have the curvature, which is defined to be the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the position function itself. And then we have another way of calculating it here, r prime of t crossed with r double prime of t, magnitude thereof divided by the magnitude of r prime of t cubed. Okay, so what our goal for this page of work is to look at the acceleration function. If we remember the unit tangent function, if say here's our unit tangent vector, then our normal vector is going to be, a unit normal vector is going to be at a right angle to the unit tangent vector. The unit tangent vector is telling us the direction of the motion. The unit normal vector is telling us the direction of the curve. The curvature calculation is telling us how quickly we are turning. It's some measure of that. And then the acceleration then has to be in the plane of the unit tangent vector and the unit normal vector. So somehow we should be able to come up with, say our acceleration is in this direction. we don't know, like I'm not looking at a specific example, but say our acceleration is in this direction. It has to be in this plane given by the normal vector and the tangent vector. So we should be able to come up with some, I'm going to call it a1 in the tangent vector direction plus a2 in the unit normal direction. So I'm just going to run through the calculations of how this is come up with. Where again, our goal is to solve for a1 and a2 here. So we start with the unit tangent function. I'm going to move this down real quick. We've got so our unit tangent function is given by r prime of t, which is the same thing as our velocity, v of t, and the magnitude of r prime of t is the magnitude of v of t, which we're going to call just little v, or this is technically a nu if I am remembering right. Yeah, that is the Greek letter nu technically, but whatever, little v is fine for our purposes here. Okay, so this shows us that our velocity function, v, equals v times the unit vector function. And if we take the derivative of both sides here, let's work this out a little bit, then what we're going to realize, so I'll add some steps in here, v equals little v, which is a function of time, times the unit tangent function, which is also a function of time. So when I take the derivative, my acceleration, we have to use the product rule on this. So we take the derivative of the first, little v prime times the unit tangent function plus little v times the unit tangent function prime. And then we're going to do some substitutions here. We look at the definition of curvature, which is the magnitude of t prime over the magnitude of r prime, which equals the magnitude of t prime over little v. And so we can say the magnitude of t prime equals the curvature times little v. And we can take this, and then we can take this and plug it in for our definition for the normal function, and which is t prime over the magnitude of t prime. So the magnitude of t prime we're replacing with k little v, and so we can then say that t prime equals kv times the normal vector. So we can take that then, and looking at our acceleration, we can replace t prime with kv times the unit normal vector, and so then we get the acceleration vector equals v prime, little v prime, times the unit tangent function plus kv squared times the unit normal function. And that gets us that my a1 that I'd given over here is v prime, little v prime, and a2 equals the curvature times little v squared. And this shows that, yes, we can write our acceleration as a linear combination of our unit tangent function and our unit normal function. Okay. If we keep going here, we're going to just, this is essentially saying the same thing. They said a1 is a in the tangent direction and a2 is a in the normal direction. So we have the component. So let's draw that picture again. If I have my unit tangent function and my unit normal function, and here's my acceleration vector, then the component in the n direction is the curvature times v squared, and the component in the tangent function is little v prime. And that's what we're saying here. All right. And we have another lemma that we're going to use. Hold on. And so now what we want to do is come up with a way of quickly calculating the acceleration's tangent component and normal component. So our lemma here is that v prime, little v prime, equals v dot a over the magnitude of v equals r prime of t times r double prime of t over the magnitude of r prime of t. And we're just going to prove that real quick. So the bottom part's simple enough. We have little v equals the magnitude of r prime of t. That's by definition. So we really want to prove this first step, that little v prime equals v dot a over the magnitude of v. So let's start with how the v dot a is going to work out. So the vector function, the velocity vector function dotted with the acceleration function equals, well, we know that the unit tangent function equals the vector function over the magnitude of v, and if we rearrange that again, then we get v, the vector for the velocity, equals little v times the unit tangent function. So we plug that in for the vector, the velocity vector function, and the acceleration we just came up with as from above, that the acceleration function equals little v prime times the unit tangent function plus the curvature times v squared times the unit normal function. So we plug those in, and we go ahead and distribute this across. So v dot a equals little v times the unit tangent dotted with v prime times the unit tangent function plus curvature times v squared times the unit normal function. Distribute that across, we get little v times little v prime times the unit tangent function dotted with the unit tangent function plus curvature little v cubed times the unit tangent function dotted with the unit normal function. Now we recognize that the unit tangent function dotted with the unit tangent function is going to be 1, and that's because they're parallel, and the unit tangent function dotted with the unit normal function is going to be 0 since they're at right angles, and so we get that this equals little v times little v prime. If we rearrange then, we get little v prime. So we've now shown that the velocity function dotted with the acceleration function equals little v times little v prime, and if we rearrange, we get little v prime equals the velocity vector function times the acceleration function divided by little v. And we know what the velocity function is. That is r prime of t. The acceleration function is r double prime of t. And then again, little v is the magnitude of r prime of t. So that proves our little lemma, and that allows us to quickly come up with the tangent component for the acceleration. Little v prime equals r prime of t times r double prime of t over the magnitude of r prime of t. And continuing on, we know now that the normal component for the acceleration is the curvature times v squared, and the curvature we had already proven in our last lecture that that equals the magnitude of r prime of t crossed with r double prime of t over the magnitude of r prime of t cubed, and then the curvature squared, well, that's the magnitude of, that's a typo, r prime of t here. And so we can cancel two of these and get just r prime of t on the bottom. Okay. Great, we're going to now, this is a lot of work that we've done just to go ahead and show how to get the components for the acceleration, the tangent component and the normal component, and now we're going to go ahead and use those in this next example where we have a particle moving with position function r of t equals negative t squared, comma t, comma 2t cubed, and we want to just determine those tangential and normal components. So to do this, I'm going to start by copying down the formulas for our tangential component, which is little v prime, which we've now proven equals r prime of t, dotted, with r double prime of t over the magnitude of r prime of t, and the acceleration in the normal component equals the curvature times little v squared, which we've now shown equals the magnitude of r prime of t crossed with r double prime of t. Close the magnitude there, all over the magnitude of r prime of t. And so now we simply need to go ahead and find all of these things and plug them all in and calculate them. So let's start with saying what is r prime of t and what is r double prime of t. So r prime of t equals negative 2t, comma 1, comma 6t squared, just by taking the derivative of r of t. R double prime of t equals negative 2, comma 0, comma 12t. Let's then get the dot product. So r prime of t dotted with r double prime of t, because we're going to need this for our tangential component. This equals, let's just write it out, negative 2t, comma 1, comma 6t squared, dotted with negative 2, comma 0, comma 12t. This equals 4t plus 0 plus 72 t cubed. Then we're going to need the cross product. So let's see. I want r prime of t crossed with r double prime of t. So I want negative 2t, 6t squared crossed with negative 2, 0, 12t. So my first component, I'm going to ignore the first components and do 1 times 12t minus 6t squared times 0, which is just 12t. My middle component, I'm going to do negative 2t times 12t, negative 24t squared, minus 6t squared times negative 2, so that's plus 12t squared, so we had a negative 24t squared, plus 12t squared is negative 12t squared, but then we change the sign to be a positive 12t squared. And then we ignore the last component for the last component, so negative 2t times 0 is 0, minus 1 times negative 2 is a positive 2. So here's my cross product. And we need the magnitude of r prime of t. So that's going to be the square root of negative 2t quantity squared plus 1 squared plus quantity 6t squared all squared, which equals square root of, I'm going to do this highest degree first, so 36t to the 4th plus 4t squared plus 1. And I don't believe this factors, so we're going to leave this just as it is. So let's go back up to the top here where I have the acceleration equals r prime of t dotted with r double prime of t all over the magnitude of r prime of t. So the dot product we said was 4t plus 72t cubed over, now the magnitude of r prime of t is the square root of 36t t to the fourth plus 4t squared plus 1. And that's our tangential component. So this we can use for any t value. So if we're looking at the position when t is 0, or t is 5, or t is 10, then we can plug in that t value here and know what the tangential component of the acceleration is. For the normal component, we still need the magnitude of this cross product. So where do we want to put that? Running out of room here. Let's go to the top right. Not the best place for it, but r prime of t, the magnitude of r prime of t crossed with r double prime of t, that equals the magnitude of 12t comma 12t squared comma 2, which equals the square root of, it's going to be 144t squared plus 144t to the fourth plus 4. And we can factor out a little bit here. So here I can pull out a 4. 36. So I'm going to have a 2 square root of 36t to the fourth plus 36t squared plus 1, all inside the square root. Okay, so I can take that and plug it in for the numerator of my normal component. And the denominator, again, is the magnitude of r prime of t, so the square root of 36t to the fourth plus 4t squared plus 1. And that's it. That's all that we're looking for in this. I am going to go ahead and show you a picture of the function here with the tangent, the unit tangent function, the unit normal vector, and the acceleration vector. Let's see. Boom. So here in GeoGebra, I've programmed in the curve, negative t squared comma t comma 2t cubed. And I've got a slider so I can look at different points. So I have a point A equals, so my curve I named R, so a point I have equal to R of B, A equals, capital A equals R of B. So I can use a slider here to change what point I'm looking at. Let's just go with about there. I'll zoom out just a bit. There we go. And I've then gotten my velocity function, my acceleration function, by taking the derivatives of my position function. And we've got my tangent vector is actually going to take a couple of steps. I'll let you guys look at this on your own for the details. But essentially we have to get the tangent function, the unit tangent function itself, and then the unit tangent vector at a specific b value from the slider above. And then I've worked out the f of t is actually the magnitude of r prime of t, and then I was having a hard time getting the GeoGebra to get our normal vector by taking the derivative of the tangent function divided by the magnitude of the tangent function. So I built up the components one at a time, and I'll leave that as an exercise for you to look through on your own. But built that up so that I could get my normal unit normal vector function, and then built my normal vector, unit normal vector from the b value from the slider above. And I'll close this out. Let's see a little bit more here. So that I could get my acceleration vector as essentially, actually built my acceleration vector separate, but we can now see the unit normal vector, the unit tangent vector, just the green one here, and my acceleration vector. We can see that they're all in the same plane, that the normal vector is at a right angle to the unit tangent vector. and so that we can see the acceleration vector as a linear combination of the unit normal and the unit tangent vector. All right. And that's it for this problem. And we just have one more exercise that I'm going to have you guys try. So this is a little bit different than what we just did, but go ahead and read the problem, give it a shot. Pause the video, and here in just a few seconds I will go ahead and have the solution written out and go through it with you. Okay, so if we want to minimize speed, we first need to find a speed function. So little v of t, not the vector function, but the speed function, equals the magnitude of r prime of t, which r prime of t is 2t comma 3 cosine of 3t comma negative 3 sine of 3t by taking the derivative of my position function r of t, which again was t squared comma sine of 3t comma cosine of 3t. I then take the magnitude of my little v of t. So again, little v of t was 2t comma 3 cosine of 3t comma negative 3 sine of 3t. I take the magnitude of that. I get equals the square root of 4t squared plus 9 cosine squared of 3t plus 9 sine squared of 3t, which equals the square root of 4t squared plus 1. I got that by using Pythagorean theorem on by factoring out a 9 in the previous line from the cosine squared and the sine squared, because cosine squared of 3t plus sine squared of 3t equals 1. Oh, hey, look at that. Made a mistake. So plus 9, because we factor that out and get 9 there. Oops. Let's make a couple of adjustments. It's not going to change a whole lot. That should be a 9. That'll be a 9. That's going to make this a 9 up here as well. And this a 9 down here as well. Make sure I got it all. Yes. Okay, so if this is my little v of t function, this is my speed function. If I want to minimize it, I need to take its derivative and set its derivative equal to 0 and look for critical numbers, and then we can use those critical numbers to determine when my speed is going down, when it's going up, and when it's minimized or maximized, all of those things. So little v of t prime equals 1/2 times 4t squared plus 9, close parentheses, to the negative 1/2, times the derivative of the inside, which is 8t, equals, I'm going to go ahead and put the negative 1/2 exponent, turn that into a square root in the denominator, and the 8t reduces with the 2 to give us equals 4t over the square root of 4t squared plus 9. Now the denominator doesn't have any zeros because of the plus 9 inside the square root. No matter what t is, this is always going to be a positive number down here. So no critical numbers due to a domain issue, but we do have the critical number that when t equals 0, that v prime of t equals 0. So v prime of t equals 0 when t equals 0, and this is the only critical number. So if I put this on a number line, I put 0 here, I look that v prime is going to be negative when we are to the left of 0 and positive when we're to the right of 0. I can see that by saying, okay, my v prime of t is always has a positive denominator, and the numerator is negative when t is negative and positive when t is positive. That tells me that my original speed function is going down when we are to the left of 0 and going up when we're to the right of 0, due to its derivative being negative to the left of 0 and positive to the right of 0. I can then plug 0 into my velocity, or function, not my velocity function, my speed function. So v of 0 equals 9. Plugging that in here. So the speed is minimized when t equals 0. The minimum speed is 9. And that is it for this lesson. Thank you so much, and we will see you guys in lesson number 5.